Good evening, everyone. We're going to go ahead and get started with our atomic structure, unit. We're starting with this term, atomos, which means not to be cut. In this video, we're going to take a little bit of time and we're going to actually look through the history of the atom. As we watch the video in class, we noticed that, the atom is so small. How do we actually know what it looks like if there's nobody who can actually say, I've looked at it, I've held it, I've broken it apart and looked at the different parts. So, start off with our central question. How did we develop, that's supposed to say we develop, the knowledge of the atomic structure? Again, looking at the fact that we don't have this necessarily, the technology, or actually these scientists that we're going to be studying didn't have the technology to find a lot of this information. How did they go about determining what the atom was like, how things are arranged, what are the parts that make it up, and so forth? The things you should be able to do at the end of this video and at the end of this first part is students will be able to give the progression in order of the atomic model. So starting from the earliest model, moving all the way to the current model, be able to actually give that information, explain the differences in each phase of the model. That includes the scientists and their experiment that they used. It's very important that you know sort of what they did so you can sort of pick out how they added to the model. Now, atomic models. When we look at this is the kind of model that we normally see. For many, they'll point out and say Jimmy Neutron. For those who may have been science before, they may say the electron cloud model. All of these things would be correct. But how do we get to this point? We see that we have a nucleus, we have these electrons, we have these different energy levels, all these things. But we did not have all these pieces of information at once. So who came up with the model? We're looking at the fact that it was different people. It was 6 men, actually more than that, but 6 main people that we're going to look at today that came up and helped us to arrive at this model that we use. The first of which we're going to talk about is a man named Democritus, or Democritus, however you want to say his name. Now, the Democritus theory is that matter could not be divided into smaller and smaller pieces forever. There had to be a point at which you could not divide matter anymore, which makes perfect sense. So there had to be a piece that was indivisible. He named the smallest part of matter atomos, which means not to be cut. Makes perfect sense. Now, this is the interesting thing. Notice that at the bottom here it says that Democritus was a Greek philosopher. Sorry, my line is crooked. What does a philosopher do? What are they known for? Most times philosophers are thinkers. They're people who are considered to be wise based on their logic and their view of how certain things work. Why do I want to bring this up? Well, Democritus was this philosopher, but there are also others who are more popular than he was. What do I mean? Aristotle. If we look back in science, one of the things that a lot of people believed for a long time is that everything broke down into the 4 main elements. These 4 main elements: fire, water, wind, and earth. This was based on the thoughts of Aristotle. Now, Democritus was around the same time, so they were contemporaries of each other. They were almost, if you could say, they were co-workers, or they could have been friends. But because of the fact that Democritus had no proof, his information was sort of cast to the side. Democritus said atoms were small, hard particles that made of the same material but different sizes and shapes, of course making up the different elements. And there were an infinite number of ways of moving and joining them together to make these compounds, make the things that we normally interact with. His idea was ignored for about 2,000 years, a little bit more. That's a problem. So remember, when we go into science, whenever we do anything, we always try to have proof. It's no longer what this person said or what that person said. There has to be some sort of proof in order for us to get started. Now, just realized I had ketchup on my shirt. It's okay. We'll pass that on later. Now, into our next model. Now, this is going to be John Dalton. Now, John Dalton did a number of experiments with gases, looking at volumes of gases, how certain gases react when they're contained, and all these different things. But with his experiments with gases, they led to this idea of the atom actually existed. And from this, he came up with what's called Dalton's atomic theory. Now, he deduced that all elements are composed of atoms. Makes perfect sense. Atoms are indivisible and indestructible particles. Atoms of the same element are exactly alike. Atoms of different elements are different. And compounds are formed by joining the atoms of two or more elements together. Now, some of this information sounds very, very familiar. If you go back when we talked about Democritus, he thought that atoms were these indivisible, indestructible particles that could be different sizes, but they were used to make up all the different things that are around us. Why is it that Dalton's theory is actually accepted? Because he had proof. Now, based on this, you get a chance to see what his model sort of looked like. Notice you have just this round ball. They didn't know of anything inside of it. They just knew that you had this thing that could not be divided any further. So, moving on. The next person we're going to come to is J.J. Thompson. In 1897, so this is relatively recent, within the past 150 years, J.J. Thompson proved that an atom was not as solid as they thought. What do we mean? Through his experiment, he found that there are some positively charged substances in there, but there are also some negatively charged substances spread out sort of like raisins in a pudding. Not a pudding that I would like to eat, but let's go with his idea. Now, this is his experiment. Thompson studied the passing of an electric current through a gas. While he was doing that, if you notice at the top of the screen, you see this negative sign here, and you see this positive sign right here. What he did is, he took this gas, had it in a tube, it's called a cathode ray tube, and he passed electricity through it. And then he turned on these charged plates. So if you notice here, we had a negative, and then we have a positive. When he turned on the charged plates, he noticed that it bent away from the negatively charged plate. Why would it do that? Well, let's take back our logic. We've heard this before. If I have two magnets sitting right next to each other, and I have a north pole and north pole, and I try to put it together, what's going to happen? Well, they're going to push each other apart. But if I have opposite charges, north and south, they're going to be attracted to each other, and they're going to want to stick. Similar thing is happening here. If the band, the electricity, is bending away from the negative charge, that must mean that there are some negative charges in there causing it to push down. So deflection towards positive plate means there's a negative charge. Now, this was like revolutionary throughout all of science. This is something that was unheard of. And so they took this information and developed a new model. Now, he could conclude that based on this experiment, this cathode ray tube experiment, that the negative charges had to be within the atom, and therefore a particle smaller than the atom had to exist. This was the model that we began to use. It's called the plum pudding model. It shows, again, that there is some positive charges in there, but it's just showing it as if the positive charges are sort of like the jelly that everything else is floating in. And within that, I have these negative charges scattered about. Now, originally he called these things corpuscles, but over time we got the name electrons. Don't know from who, but this is the model that we began to move towards. So if we go back to the beginning, we had just a ball, this indivisible little piece of matter. Now we're starting to see that it actually is divisible, and there are these electrons that are floating around inside somewhere. Now, taking a step further, we're now going to go to Ernest Rutherford. Ernest Rutherford, in 1908, was an English physicist. He had an experiment that he was doing dealing with radioactivity, where he shot tiny positively charged particles at a thin sheet of gold foil. Now, imagine setting this up sort of like a gun. Little gun shooting only positive particles. Or like helium atoms, helium nuclei. So he took these and he's shooting at this gold foil. What did he expect to happen? Well, he assumed that since there's this positive jelly, I guess you would say, and the electrons are sort of there floating around, that the positive particles would go directly through and he'd have no problem. This is an idea of what he's looking at for the whole entire experiment. You have over here your source shooting in at the foil, and then this is a detector all the way around. So it's set up so you'll be able to determine where exactly the particles go. Now, most of the positively charged bullets pass right through sheet will go forward without changing course. But some of the particles, however, bounce back. They either bounce to the side, they bounce directly back, and he had to figure out that they hit something solid. So, since he knew, again, electromagnetic force, positive is going to repel positive, he knew that he had to be hitting something solid and positively charged. Atoms were not, as J.J. Thompson had considered, a pudding filled with positively charged material. Rutherford concluded that based on this experiment, that an atom must have a small, dense, positively charged center that repelled his positively charged bullets, if you will. Now, this is going to be sort of an idea of the model that we're now looking at. So before, it was just positive randomness inside. Now we have this solid positive charge here with the negatives still scattered about on the outside, allowing most of them to go through, but some of them to get sidetracked. He named the center of it, of the atom, the nucleus. That's where we get that term, where we use that term, at least in chemistry. Now, two more models to go, and then we're set for the evening. Now, Niels Bohr. Niels Bohr was a Danish scientist, and you notice that a lot of these things are right after another. J.J. Thompson, I believe, was in the 1890s, late 1890s, and then Ernest Rutherford, 1908. Now we're in 1913, and Niels Bohr proposes an improvement. Looking at his experiment, he found that the electrons were actually in specific energy levels around the atom. What do I mean? Take a look at these diagrams. According to Bohr's model, the electrons move in definite orbits around the nucleus, sort of like we have the planets go around the sun. So we can predict, based on his model, that they should be within a certain level, a certain space around the atom itself, or the nucleus. With this information, he began to actually look at a couple other things, especially dealing with light. And light, that's actually a fun thing that we'll get a chance to hopefully do a little demonstration with. Now, Niels Bohr was our second to last, and the last one, my favorite, is our current model, which is going to be called the electron cloud model or the wave model. Now, this is the one that looks sort of like a flower, like some people were saying maybe had a strange appearance to it. This is going by a man named Erwin Schrödinger. Now, if you've heard of any scientific theories before, and you've heard of Schrödinger's cat, this is the man that they're talking about. Basically, looking at the information of what we had and then the model that we used, it all was based on what's called Newtonian mechanics, based on a very, I guess, one-dimensional setup. But Erwin Schrödinger, through a lot of complicated calculations, you notice that he did a lot of calculated math to figure this out, figured out that the electrons actually move in more of a wave-like pattern. This allows them to move and to be at any different location within a certain amount of time. Going back, these areas that you see sort of spinning out and going in these different directions are areas where you would be likely to find the electrons. So, in the end, it looks sort of like a cloud. That's why we say electron cloud model. So, based on the electron cloud model, the electrons move in 3D pathways billions of times per second, constantly moving randomly all over the place. And so we describe it as electron cloud. The location of the electrons depend on how much energy the electron has. So the further away it is, usually is going to be the more energy that it has. This is where we wrap up this part of Unit 5, the first section. Take a moment, review the information, and when you come into class tomorrow, be ready to defend and to explain what you're seeing are the differences, the main differences of each of these models. Have a good evening and look forward to seeing you in class.